Hey, I'm Courtney Waterman, your tutor. Lover of anime, manga, and math. And you just tuned into another session of Tutor Me Sempai. Welcome back, everyone. Today we're jumping into a 9th grade topic, simplifying radicals with variables. Now, if you're new to my channel, I've put timecodes in for this video in the description box below, so use that to skip ahead to whatever part of the video you think is most interesting. As always, if you have any questions about what you see here today, or even your own homework, feel free to put in the comment box below, or visit me on my Facebook page at Tutor Me Sempai and tell me all about it there. Now we have a lot to cover today, so hit the like button, smash the subscribe button, and let's get started. Before we jump into simplifying our radicals with these variables, there's a few disclaimers I'd like to get out the way. This video will be made under two very important assumptions. The first, you should know what a radical is. And the second, you should know how to simplify what I call constant radicals. Those are going to be the radicals without variables. If any one of these two or both are not true for you, I have a video on each of these topics you can find right here. Be sure to check out those videos and get the relevant information, because that's going to make this video make a lot more sense. Once again, this video we made under these two assumptions. You should know what a radical is, and you should know how to simplify a constant radical. All right, now that we've talked about that, let's jump into our video for today. So assuming you grasp the concept of simplifying your constant radicals, the very next step is to add variables into the mix. Here we have the square root of x to the 5th. And I want to let you know, if this scares you, don't worry. This is actually going to be so much more simpler than what you did previously with the constant radicals. And I'll show you how. We're going to use everything we know about radicals in order to simplify this. So the first thing we know is we can break down the radicand into its factors. When you have a constant, you have to do your whole tree unless you know what the factors are. But whenever you have your variables like this with your exponents, you have a little bit of freedom. So I'm going to break up this into its factors in a particular way, and I'm going to explain why in just a minute. So x to the 5th can be broken up into x squared times x squared times x. And if it's not apparent why I broke it up this way, remember what we wanted to do for our constant radicals. We wanted to isolate the perfect radicals and separate them from the non-perfect radicals, right? I still want to do that for variables. So this is going to be a square root. Although we don't necessarily have to write the 2 there for the index, we understand that 2 to be there. So that 2 is going to be what I'm shooting for. I want to make my exponents the same value as this index. Now, if I can break up our radicand into having different factors with this same index value, I'm going to do that, because that is going to guarantee that I get a perfect radical. In this case, it will guarantee that I get a perfect square that's going to simplify very easily. So now that we've broken it up under the radical, let's give each one of these factors their own radical. I wrote the 2 here just to reiterate that this is a square root, and you see I'm trying to match up the index with the exponent. If these are equal, this is going to cancel out and you're just going to get x, or whatever the variable may be. In this case, it's an x, so you're just going to get x. And you see, this is the same story. So it's going to be times x. Everything is connected through multiplication. We're not losing anything here. So these two cancel out. However, this doesn't. There's nothing here that will go away, so we bring it down as is. So that's going to be the square root of x. And when we multiply all of these together, you get x times x, which gives you x squared, times the square root of x. So we start with the square root of x to the 5th. We break it up into its factors, but we have the freedom to choose what the factors are. Since this is a variable, we can do that. However, this is our next step. We want to take all of the factors and give them their own radical. This is going to be the same exact thing we did as with the constant radicals. Now that we've isolated our perfects, we can just simplify them as is, and anything that's left over stays in that radical. Combine them to your final answer, and voila. I told you this is going to be so easy compared to what we did for constant, just because you have so much more freedom when you have these variables. Let's look at another example. Here we have the fourth root of x to the 7th times y to the 15th. Now this also may look very scary, but remember, we want to use everything we know about radicals in order to simplify this. So take your time, one step at a time, and I assure you it is going to be simple. The first thing I want you to do for this drawn out method is to separate your x's and y's. Remember, they're multiplied together, so you can give them their own radical off bat. And that's going to make understanding this so much more simple because we don't have to worry about doing them at the same time. So this is going to be the fourth root of x to the 7th times the fourth root of y to the 15th. Now that you've broken them apart, focus on each variable one at a time. Remember, the goal is to not get confused. So I'm going to rewrite this one as the fourth root of x to the 4th times x cubed. Remember, I want to break down a radicand into its factors, in which one of those factors gives me an exponent with the same value as our index. If you can do that, that guarantees you have a perfect radical. So whatever's left over, you just leave it alone, and we're going to do the same thing for y. So this is going to be the fourth root, slightly bigger one here, and it's supposed to be a 4, not a y. This is a 4, of y to the 4th times y to the 4th times y to the 4th times y cubed. So you see, we're breaking down each one individually, right? Our x's first, then we break down our y's, and the process is going to be the same. So going back to our x's, we can break this up into its own radical, right? So that's going to be the fourth root of x to the 4th times the fourth root x cubed. Same thing for our y's. This is going to be the fourth root of y to the 4th times the fourth root of y to the 4th times the fourth root of y to the 4th times the fourth root of y cubed. And that's a cubed. Now we can identify all of our perfect radicals, simplify those first, and then bring down anything left over afterwards. So this is going to be our x, right? Because it's x to the 4th. And this is a fourth root, so it simplifies perfectly. This is going to be left as is. So it's going to be the fourth root of x cubed. It doesn't break down any more than that. This is going to be y. That's going to be y. That's going to be y. And this is as is. So you have a fourth root of y cubed. Now forgive me, I ran out of space, so I'm going to have to erase something a little bit earlier so we can continue. So if you need to retrace your steps, hopefully you're following along, but you can always rewind the video to see what I erased. So I moved that result we just got a little bit higher to give us more space. So let's continue what we're doing. I want to keep our radicals at the end because that's just common practice. So let's move our variables up front and our radicals at the end. So we have 1x here. We're going to combine that to nothing because it's by itself. But we have 3 of these y's multiplied. So that's going to be times y cubed. Then you have times our radicals, right? We have x cubed under this fourth root. And we have a y cubed under another fourth root. And just like you broke them apart, you can put them back together again. So this is going to be x times y cubed times 1 radical, fourth root of x cubed y cubed. So this is the long drawn out process, but you see why it works. Using everything we know about our radicals, breaking things up, separating, manipulating the factors as we want for these variables is going to be so much more simple in order to get our final result than when we had our constant radicals. But now that you've seen this long drawn out method, let me show you how we can do this a lot simpler. Here's our shortcut. So we're going to be tackling the same exact example we just did. However, we're going to be doing it with our shortcut, which is going to save you a ton of writing. So the one thing you're going to need to know for this shortcut is division. Division is going to be the key. This index, we're going to divide it into our exponents. How many times does this index go into each of these exponents? If you can answer that, you can do this shortcut. So let's see how this works for the x's. But before we begin, I want to still break this up into our x and y so no one gets confused as to what we're doing. You don't have to do this step for the shortcut to work, but I want to just drive home exactly how this is working to make sure you get the shortcut in all of its glory. So how many times does 4 go into 7? Well, 4 goes into 7 one time with a remainder of 3. Well, that one time is going to mean that we have one x outside. And that remainder of 3 means we have 3 x's inside. So we have something like this. X times x times x inside. So 1 outside, 3 inside. How about y? 4 goes into 15 how many times? 4 goes into 15 3 times, right? With a remainder of 3. So that means you have 3 y's outside and 3 y's inside. So let's simplify all this. So you have x times the, and this is a 4th root there. Almost forgot that one. Again, x cubed times y cubed times 4th root of y cubed, and you can combine your radicals. So let's do that all in one step. X cubed, y cubed. You see we have the same exact answer, but we did it so much faster. So that's the shortcut. We're going to use our index, divide it into our individual exponents, and whatever our remainder is, you can just leave it in the radical. However many times it goes into our exponent, that's how many of those variables are outside the radical. But one cool thing about this, you don't even have to do this step here. You can go straight from here to here. Let me show you one more example to drive home this point. Let's try to use our shortcut without doing all the extra steps. I still want to break this up into its different components. So this is still going to be the cube root of 16 times the cube root of x to the 8 times the cube root of y to the 10th. But let's see if we can really maximize our shortcut to minimize how much we're actually writing. So we're going to come back to that 16. Let's jump straight into our x's. 3 goes into 8 how many times? Well, that's going to be 2 times. And how many are left over? 2 is left over, right? So we have 2 x's outside and 2 x's inside. So you're going to have something like this. X squared, cube root of x squared. How about our y's? 3 goes into 10 3 times with 1 left over. So you're going to have something like this. 3 y's outside times the cube root of y. Only 1 y is inside. So you see, we don't even have to do any of those other steps. We can go straight into this. But we're not done. We still have to find the cube root of 16. Now this is going to be going back to what we did in our last video when we talked about constant radicals. And if you remember your perfect cubes, you know that 16 can be broken up into 8 times 2, in which 8 is going to be your perfect cube. So this is going to simplify into 2 times the cube root of 2. This was what we covered in our previous video. Now we combine everything. Everything on the outside gets combined and everything on the inside gets combined as well. Let's put our constant out front. So we have a 2 times x squared times y cubed. And now our radicals. Cube root of 2 times x squared times y. Now we've simplified, although it doesn't look all that simple, we've simplified this radical into this. So you see, the beauty of our shortcut is that we can use this index to directly simplify our variables. That was something that we couldn't really do when we had constant radicals, but it's something we can take advantage of when we have these variable radicals. There's another reason why this shortcut works, and it becomes a lot more apparent when you take things from their radical form into their exponent form. Let's go back to our first example. That's going to be the square root of x to the 5th. What is the exponent form of the square root of x to the 5th? Well, that's going to be x to the 5th raised to the 1/2. But whenever you have an exponent raised to another exponent, you can just multiply those exponents. So you get something like this. X to the 5/2. So remember, our index here is a 2. Although we don't write it, our index is an understood 2. So when we said how many times does 2 go into 5, we're really just taking advantage of the exponent form without having to convert it to our exponent form. So we can rewrite our x to the 5/2 to be x to the 4/2 times x to the 1/2. This is what we're left over with, and this is how many times it goes into it perfectly, right? That's going to be x squared times x to the 1/2. 2 goes into 5 2 times with a remainder of 1 left over. Well, x squared is going to just be x squared, and x to the 1/2 is going to be your square root of x. So once again, our shortcut is really just taking advantage of our exponent form without having to convert it to exponent form in order to see it. Before we wrap up this video, there's one more special note that I neglected to cover throughout this video, and that's the absolute value of some of these variables. Because variables can be positive or negative, we don't know what they are. Absolute values will have a play when we're talking about simplifying these radicals. But they don't always come into play, but there are some circumstances in which they do. And sometimes your teacher might require you to put absolute values. I didn't do it for some of my examples where I should have, but I want to let you know that special note now. Let's look at this example here. We have the square root of x cubed. Now, if you follow on with this video and you do our shortcut, you know that that's going to be this. Because this is a square root, we know that whatever is out here has to be positive. You can't have a negative come out of a square root. So in order to make sure that this is positive, we have to add the absolute value. When you have the absolute value, it doesn't matter what your x is, negative or positive, you're always going to look at the positive version. But this is not going to be the case for all radicals. This is only the case when you have even radicals and you have odd exponents. This is a 1 here. So if you have an even radical and an odd exponent on the outside, that is going to require you to have an absolute value. If you have an odd radical, it doesn't matter. You can take an even or an odd out of it. If you have an even exponent, it won't matter either, because whenever you raise that even exponent, the negative is going to fall out anyway. So the only case you have to worry about this absolute value is whenever you have an even radical and an odd exponent on the outside. Both of those two combined can't guarantee that you're going to have a positive out here, so throwing in your absolute value is going to save the day. So something like this is going to require an absolute value. Once again, this is even, right? And 4 goes into 5 one time. You have an odd exponent here, and you have 1 left over. It doesn't even have to just be ones. Let's say instead of this 5 here, you had 13. Now, 4 goes into 13 how many times? Well, that's going to be 3, and you have what left over? 1 again. But for this, we need to make sure that this is positive because this is a 4th root. That is why we add absolute values. So our special note today is whenever you have an even radical and an odd exponent outside your radical, make sure that it gets an absolute value just to be on the safe side and to technically be correct. So I hope you're following today's examples, and I hope you see that simplifying your radicals with variables can be so much simpler than you're simplifying your constant radicals. As long as you understand how to manipulate your factors and use your index, this can be a rather simple process. Once again, if you have any questions whatsoever about today's stuff or even your own homework, feel free to put it in the comment box below or visit me on my Facebook page at Tutor Me Sempai and tell me about it there. If you haven't done so already, remember to leave a like. It really helps the channel by letting YouTube know that you found some value in this video, and it can also be valuable for somebody else. So hit that like, smash the subscribe, hit the notification bell, and share this video with a friend. Well, that's all the time I have for today. I'm really hoping this helped with your homework. I'm looking forward to seeing you again next week. I'm Courtney, and this has been another session of Tutor Me Sempai.